Hello and welcome to helpyourmath.com. In this video, we're going to look at evaluating and graphing piecewise functions where the pieces are linear pieces. First, let's review what a piecewise function is. A piecewise function is a function comprised of pieces of functions. The domain is specified within the function itself. It's behind the piece that it applies to. So for example, if we have f of x is equal to, usually we recognize a piecewise function because there's a left brace and only a left brace. And then it will have functions. So it might say x minus 4. So this here, f of x equals x minus 4, that is a linear function, right? It's a line, it's going up like this, something like that. But what makes it a piecewise function is it tells us where either a stopping point is, a starting point is, or both a stopping and starting point. So it might say x is less than -1, in which case this piece would stop at -1. Now, something else about this particular piece, it says that x is less than -1, meaning we don't include the value -1. What do we do in graphs when we want the graph to go to this point, but we don't want to include that actual point? We use an open circle. So this indicates that this piece stops, and because it's just less than, it's going to be an open circle at -1. Okay, and then we have probably another piece. Maybe this one is 2x plus 3, and this one will start where that one stops usually. So usually there's no lapse in the domain. The domain will be all real numbers. It's just those real numbers are split between 2 or 3 or 4 different graphs. Now what does this look like? 2x plus 3. That's going to be the line f of x equals 2x plus 3 would have a y-intercept at 3. And it would be going up from left to right, right? It has a rise of 2 over 1. This one starts at -1, so it might be, I don't know, up here somewhere. And this one's going to be a sharper increase than our original one. So this would be an example of a piecewise function. Notice that I keep using the word function. A function indicates that it will pass the vertical line test. So that's why we generally will see an open circle like this and a closed circle. So that way if I drew that vertical line, it's only hitting the graph at the closed circle. That open circle indicates that there's no actual point there. Okay, so let's look at an example of what we might see. We're given g of x and we want to answer each part. So here's my function here. This is a piecewise function and it has two separate pieces. Each piece is a straight line, but if I was to draw two straight lines in my coordinate plane, you'll notice that this would fail the vertical line test here and here and here. Actually, it's going to fail it everywhere. So that's not a function itself. That's why there's restrictions on the domain. This piecewise function is going to look like this line, 1/2 x plus 6, until x is -2. So anytime x is a value less than -2, that's the piece we're looking at. If for values that are greater than or equal to -2, we use the bottom piece. So it depends on what we're given. Will kind of dictate to us which piece it belongs to. And I like to name my pieces. This is my top piece I call piece 1. My bottom piece I call piece 2. So we want to evaluate these given values. The first one is g of -4. So we have to make -4 a true statement right here. Where is -4 a true statement? Is -4 less than -2, or is -4 greater than or equal to -2? Nope, it's not this one. It's this one. So this is where -4 is in the domain. It's less than -2. This is the piece we plug it into. We plug it into piece 1. So when we plug it in, we get 1/2 times -4 plus 6. Half of -4 is -2, and -2 plus 6 is 4. So this would be the ordered pair, -4, 4. This ordered pair is a solution to g of x. What are we looking at next? We're looking at g of -2. So again, where do we plug in -2? Where does it make a true statement? So we're going to go back up here. Is -2 less than -2, or is -2 greater than or equal to -2? It is this one here, meaning it's a solution to the second piece, the bottom piece. So we're going to plug in -2 only where it makes a true statement based on where the domain is for each piece. So we plug it in, we get -3 times -2 plus 1. -3 times -2 is 6, and 6 plus 1 is 7. So another point, another solution to g would be -2, 7. Okay, lastly, what do we have? G of 0. So where is 0 where does it make a true statement? Does it belong in the top piece, piece 1, or the bottom piece, piece 2? This would go in the bottom piece because 0 is greater than or equal to -2. So we're only going to plug it into piece number 2. This would give me 3 times 0 plus 1. 3 times 0 is 0, and 0 plus 1 is 1. So this is the ordered pair 0, 1. Okay, when we go to graph this, so we've completed part A, we've evaluated, yay, but now we need to graph. Remember what we're graphing. We're graphing two pieces of lines. So when we have a piece of a line, there's all sorts of different geometric names. These are called rays. We're going to graph a ray, which is piece 1, and a ray, which is piece 2. To graph a line or a part of a line, you must have at least 2 points on that line. So if we look at our top line, 1/2 x plus 6, do we have 2 points that are on this line? And the answer here is no. We have 1, right? This was the only one, this -4, 4, that was part of that top piece. And that's okay. We only actually want that 1 because we specifically actually want to choose another point. And this point happens to be the end point, but the end point is not included. How do we represent that we want it to end here, but we actually don't want to include it? We use an open circle. So when I go to evaluate this value, I can't say g of -2 because g of -2 belongs in piece 2. So what I like to do is I do -2 and I just put it in a circle just to indicate like there's going to be an open circle here. And now I'm going to evaluate -2 at the top piece. Why do I want to do -2? Because that's where the domain ends. So I plug in -2, I get 1/2 times -2 plus 6, and that would be -1 plus 6, which is 5. So this is the point -2, 5. This is the end of piece 1. -2, 5. To indicate it's the end of piece 1, I'm using an open circle because it's not included in the function, right? If I put a closed circle and then I'm going to graph the other -2, it's going to fail the vertical line, the vertical line test. Okay, so we have this, and we also have -4, 4, -4, 4, and we can fact check this, right? This is a line. Its slope is 1/2. So if I go up 1 over 2, right, rise, run over 2, I do end up at that open circle. I can graph another point by going down 1 and to the left 2. Using a straight edge, you want to connect these points. Notice that -4, 4 and this point, what's that, -6, 3? Those are points that are actually on this piece, so we do use closed circles to represent those. The only open circles are where there's the breaks in the domain and we have the just greater than or less than. And we're going to use a straight edge to draw these in. Gorgeous. Okay, what about the second piece? So the second piece is also linear, so I need a minimum of 2 pieces. I specifically want -2, which I have right here. So this piece starts at -2, 7. -2 up 7 would be up here. Notice I use a closed circle because it is included in the second piece. Notice that we will pass that vertical line test with the closed and open circle. What else do I have? I also have 0, 1. And we can fact check me, right? I want to make sure that I have the right answer. I don't like having wrong things on here. -3, it's a slope of -3 that's going down 1, 2, 3 to the right 1, down 1, 2, 3 to the right 1. I do end up there, so I feel pretty good about this. Using a straight edge, you do want to connect these. This is the one I have a really hard time with because I can't get a good angle. Okay, now we all know I'm pretty bad at drawing graphs, so I did actually do the real graph there, so we don't have to look at my horrendous work. But there we have the piecewise function with nice graphs, and that's what it would look like, this particular function. Let's try this again. Here we have f of x. F of x, where's the break in the domain for f of x? So where is one graph ending and one beginning? At x equals 1. See that here with our domain? X equals 1 is where the magic happens for this graph of f. Okay, so the first thing we're going to do, we're going to evaluate f of -4. Where is -4 going to fit in the domain? Is it less than or equal to 1, or is it greater than 1? It is in, I'm going to call this one piece 1 and this one piece 2. It is part of piece 1, right? -4 is less than or equal to 1, so I only plug it into the top piece. That would be 2 times -4 minus 3, that's -8 minus 3, which is -11. Bad news for me. It's okay. So we have the ordered pair -4, -11. What do we have next? F of -2. So f of -2, which one does -2 belong to? It belongs to the top piece, right? -2 is less than or equal to 1, so we plug it into the top piece. That's going to be 2 times -2 minus 3, that's -4 minus 3, which is -7. So this is the ordered pair -2, -7. Lastly, we're plugging in 0. So f of 0, where does 0 belong? 0 also belongs to the top piece. Oh, we have nothing from the bottom piece. Sad day. Because 0 is less than or equal to 1, this would be 2 times 0 minus 3, which would be -3. So we have the ordered pair 0, -3. We could graph these three. So these 3 points all belong to the same piece. They all belong to that top piece. But what is a crucial point that I need from both pieces? The end point. So the one I need is I need 1. I'm going to go ahead and plug in 1. And where is 1 true? It's in piece 1, right? Because 1 is less than or equal to 1. So this would give me 2 times 1 minus 3. That would give me 2 minus 3. And we would have 1, -1. Okay, so I've answered part A already, but now we're working on the graph. I want to graph each piece. Each piece should be part of a line where one stops at 1 and the other starts at 1. So I'm going to go ahead and graph 1, -1 down here, and I use a nice closed circle. Now I'm going to graph some of these other points. I don't need to graph them all. In fact, -4, -11 is not even going to fit on my graph. But 0, -3 will, and -2, -7 will. So I see one piece looks like a nice line down here. Oh dear. We can check with the slope. The slope is 2. So to get from one point to the next, I should be going up 2 over 1, up 2 over 1, up 2 over 1. But it stops at 1. For the other piece, I don't have any information. That's too bad. I do need to know where it starts. So it starts at 1. 1 is not included in the second piece. So I can't say f of 1 because that would be a false statement and that would bring me back to here. I just do 1 with an open circle around it because this is the starting point of the second piece. This is going to be -2 times 1 plus 5. -2 plus 5 is +3. So there's going to be an open circle here at 1, 3. 1, 3, open circle. And now I can use the slope to find another point, or you can just plug in a number that's bigger than 1, whatever you want to do. I'll use the slope. The slope is -2. It's telling me go down 2 and to the right 1, down 2 and to the right 1, down. Okay, that's probably enough. And we're going to use a nice, and again, this is the one I have a really hard time with, but there's the actual graph, the much better looking graph than what I can do. So that's what this particular function would look like. Notice again, this will pass that vertical line test because there's only one point at +1 where the domain breaks. Okay, one more example to really drive the point home. In this example, we're looking at h of x. H of x is a triple threat. We have 3 separate pieces on h of x. So that means we're dealing with 3 different pieces of graphs. So we should see one graph, a second graph, and a third graph, all distinct, no overlap between the graphs. Let's start with part A. We want to evaluate h of -3, h of 0, and h of 2. I'm going to go ahead and just label these. My top piece, I'm going to call piece 1, piece 2, and piece 3. Okay, so we're starting with h of -3. So where does -3 fit? It fits in the top piece because -3 is less than or equal to -3. So plugging in, we don't actually have to plug in, there is no x, so it's just -3. When we plug it in, it equals -1. So we end up with -3, -1 as that very first point. Next, we're looking at h of 0. Where does 0 fit in the domain? 0 is going to go in this middle piece, right? Because -3 is less than 0 is less than or equal to 0. Yes, 0 is less than 0. Perfect. We plug into the middle piece. We have -1/3 times 0 plus 4. This is just 0. And we end up with 0, 4. Lastly, we have h of 2. H of 2 we're going to plug in. Where's 2 go? 2 is greater than 0, so it's going to go in the bottom piece, right? It doesn't make sense up here. 2 is not less than or equal to -3. It's not in between -3 and 0. It is there where the positives are. X is greater than 0. We're going to plug in, we get -2 plus 4. -2 plus 4 is 2, so we end up with the ordered pair, 2, 2. Okay, that's part A. Now we want to graph this. And again, we have 3 distinct pieces, so we need 2 points from each piece, or at least 2 pieces of information from each piece. Let's start with piece 1. Piece 1, what do we know about it? We know it's ending at -3, and we already have the ordered pair, -3, -1. We can go ahead and graph that, and then we can Well, yeah, we probably want to go ahead and graph that because let's see what happens. We have -3, -1. This piece 1, is just h of x is equal to -1. That's a special type of linear equation because that is a horizontal line where no matter what we plug in for the x value, we're going to end up with -1. The key thing to know is that it ends at -3. But if we plug in -4, it would have -1. -5 would be -1. So it's a horizontal line at -1 ending at x equals -3. How about piece 2? What information do we already have about piece 2? We have one endpoint. Now, with a middle piece, this is the first time we've seen a middle piece, you know which pieces or which points you want to use because you want to use -3 and 0. We already have 0. We plugged it in right here. So we already have 0, 4. We would like to know where this particular piece starts. -3 does not belong to this piece. It's not in the domain of this piece. But we will represent it with that open circle, right? So I'm going to say -3, I'm going to put it in open circle and plug it into the middle piece so we know where the beginning of this piece is. That's -1/3 times -3 plus 4. This is +1, and 1 plus 4 is 5. So here we're going to end up with another piece at -3, +5, where it's not included. So we can go ahead and graph -3, +5, open circle here. 0, 4. We can double check our work. The slope is -1/3. That would be down 1 over 3. Perfect. No more points though, because that's it. Those are the end points. So anything that's a solution to this middle piece lies between -3 and 0. We're going to connect those with a nice straight line. That's the middle piece. Notice the middle piece, there's no arrows on it. It starts and stops definitively. Unlike the other pieces where it's less than something, but no greater than. Okay, piece 3. What information do we have about piece 3? We have one point. We have the point 2, 2. What other point do we need for piece 3? We need the 0, right? We need to know what this is. That is not part of this piece, so I'm going to plug it in carefully. I'm going to say, okay, it's going to be an open circle at 0. -0 plus 4 is 4, so there's going to be an open circle at 0, 4. Wait a minute. There's already a point at 0, 4, so I don't need to worry about this. One piece stopped here. This piece starts here, so we got lucky there. We don't need the open circle. I'm going to also plug in my 2, 2, and we're going to connect with a nice straight line as best we can. I didn't make a pretty graph of this one, so I'm really trying hard to make that perfect. So notice that pieces 2 and 3 have that one point that overlaps, and that's okay. You don't have to do an open circle on top of the closed circle. It's just a closed circle. It still passes the vertical line test. It's all good to go. You can clearly see there are 3 distinct lines here, right? Or pieces of lines anyway. All right, I hope this helps. Thank you so much, and thank you for stopping.